So now the only thing about this is just a plinko, just like dropping it from one spot. Okay, so it's going to drop here. It's going to either go right or left. It's going to go here. It's going to go right or left, and it's going to drop into the bottom. Okay.
Wow. Whoa.
Now we don't want 23 rows. We only want 5 rows. 5 rows. We could do that later if you want to see it, but there's 5 rows. So 1, 2, 3, 4, 5. Okay. Oh, dang it. Yeah, it's not going to get it.
Middle.
So it would be tougher to go right versus maybe right, left. There's going to be a lot of possible ways of getting it to the middle.
It's going to hit 3. Yeah, drop it 4.
Oh, there was one.
Whack.
3.
No.
4.
1.
Wow.
Send
Definitely 1.
It's just like infinite amount of waves.
Okay, so let's talk about that. That again, after a ball drops here, there would be one way to go left, and there would be one path of going just right. So that'd be after the first bounce. After the next one, there's how many paths to get here? Well, you got to go left. So there's only one path you could take to end up in this position. How many paths are there to end up in this position over here? There's only one. Now, how many paths are there to get here? You could go left, right, or right, left. So there's 2. So then the next row, again, there's how many paths to get here? There's 1 path. How many paths are there, do you think, to get to here?
3.
And I'm going to draw them. So you could go left, right. You could go right, left, or you could go left, right, left to end up there. There would be 3 paths to get there, 3 paths to get there, and 3 paths to get there. So it is Pascal's triangle. Okay? Now, really, what we're talking about here is we're talking about the number of trials. 1, 2, 3, 4, 5 trials, and each trial be it either left or right? It's like a binomial choice. Okay? Whatever k is. Let's say we want 1 success, and it's going to be P times Q, and that would give you your probability. Okay? But in terms of number of paths, since it's equally likely, this is the distribution shape that we're going to have. Okay? Now, what happens if I do this? Let's say that success then is going which way?
Right.
Correct. So like I'm making it tilted more to go towards the right. So success is going to the right. So your chances of having a left when it's a probability of success of 0.8 isn't going to be very high. Oh, that was close.
No. Here it comes. Oh. There it is.
We'll stop when there's 1. We got to get 1. Come on. Oh, there's a lot of them that are close.
It's already been 800.
What are the chances of it bouncing left 5 times in a row?
0.8 to the 5th.
To the 5th, right. So we'll stop it. Maybe we'll...
Oh, the last one! Woohoo!
All right. So that would be a practical application for, a binomial situation. Okay. So let's look at our distribution maybe a little different way. So let's say that we've got 5 trials. Let's say our probability of success is 0.5. This is going to be what the shape would look like according to the binomial distribution. Okay. Again, if we change it into what we had 0.8, didn't we? So 0.8, now you're going to have a probability of 0 successes, very low, but the probability of 4 or 5 successes is a lot higher, right? So they're different shape distributions, right? So we're going to play around with this. We have another problem that's coming up, I know, that has a number of trials is 30, and the probability of success is 0.56. What kind of shape would you say that distribution is? It's symmetric. Now, what if I change the probability here to like 0.9? Now, that's clearly not symmetric because you got to remember that you have 0 successes over here. You got a really, really skinny bar here, really, really skinny bar at 1. So you would say that you've got a tail far to the left, so you have a skewed left distribution. I could even make it more skewed to the left. Okay? So let's write down a couple things about that. So if the probability on a binomial distribution is 0.5, then we are going to have a symmetric distribution. What if your probability is less than 0.5? Your chances of success is like really small. You're probably going to have a lot of 0 successes or a lot of 1 successes, right? So this would be skewed, correct. And this would be skewed left. Okay? There's really a very simple formula, and I'll go back on some of the ones that we did. There's a really simple formula for the mean and standard deviation. The mean's really simple, n times p. Now again, this only works for binomials. Like maybe we had a distribution earlier in the chapter that wasn't binomial. You're going to have to use a different formula. Remember that formula? That's your formula for the expected value or the average of any probability distribution, right? This is the one that you could use if it's binomial. Shortcut, it's easy. Okay, formula for the standard deviation, n times p times q.
It's Q.
What's q, guys? Tell them. And it would be 1 minus p, probability of a failure. So let's do this. Okay, here's the example that I like to use. That I put somebody that's a 70% free throw shooter at the line. That means their chances of success is 70%. What would you expect the average of the distribution to be? N times p. N is 10 shots. Probability of success is 7. That's going to be the mean of the distribution. So does that mean he's going to make 7? No, he could make 6 or he could make 8. But that is, in this case, the highest bar and the mean of the distribution. That's what it means. Okay. So then the standard deviation here would be n times p times q. So go ahead and calculate what that guy is. Probably should be this. Just double check it. 1.49? 1.44. Okay. Now again, that's a measure of spread, and we're going to do a little application of it here in a second where you have to use that in your problem.
What is Q?
Q would be the chances of a miss. So this would be the chances of a make. This would be the chances of a miss. 1 minus p. Okay. Questions so far? Okay, let's work on our notes from last Thursday now, last Wednesday. So we stopped about right here. Okay, so we know this, we just went through this. Let's talk about that example at the bottom here. So, in Pittsburgh, PA.
Yeah, no, we're at the first, we're at the, like,
Okay. Okay, so this is a table. This table is in the back of the book. Okay, so you can use that table in the back to make your probability distribution as well. Okay, so you're going to go ahead and open up the back of your book. It's going to be in a appendix. So I think that it's like A8 or A10. So for example, your probability of success at the top. So if we had a 0.25, there's your probability of success. And maybe you have a situation where you have 6 trials. So here would be 6 trials right here. And so underneath that, that would be your table that would give you your probabilities for 0 successes through 6 successes. So what's the probability that x would equal 3 using this table? It would be 0, 1, 2, 3. It'd be 0.132. So you don't even have to type it into the calculator. You can just look in the table in the back, and it gives you those probabilities. Everybody understand what I'm talking about here? 0.132. What's the chances of 4 successes or more? Well, it's going to be this one. So 0, 1, 2, 3. It's going to be that one, and that one added up together, right? So that would end up adding up to 0.037. And again, really, what did I do here? I added the probability of 4 successes to the probability of 5 successes to the probability of 6 successes out of 6, right? So it's really nothing crazy. Just they got it printed out for you. Could you use this table all the time? No, because they only give a limited number of probabilities of success. So we couldn't have done the 0.62s or 0.58s or whatever, because they don't have those. So what do they go to? They go to 20 trials, right? So again, this is a limited, but you could use your table to get some quick probabilities, okay? That's all that's it. That's all that's about. Question? This is just a review of how to use your calculator. This gives you a specific value, right? This gives you the entire table. You good? Okay, so let's do this one now, okay? And use our mean and standard deviation and do a problem with that. So there are 30 days in June. Okay, so about 56% of those days we're going to expect to be cloudy. So it says find the mean, the variance, and the standard deviation for the number of cloudy days during the month of June. So you have to kind of think as success in this case is that it's cloudy because they're giving us the probability of 0.56. It's a 0.56 chance of being cloudy. So the first day is either cloudy or not. Second day is either cloudy or not. Third day is cloudy or not. So this is a binomial situation where we could make a table to figure out the chances that the number of days cloudy is 4 or the number of cloudy days is 6 or whatever. But we're interested in the distribution, right? So what is the mean of the distribution? Number of trials, which is 30 times 0.56.
16.8.
There you go. 16.8. Okay, now again, does the mean have to be a specific value of the random variable? Could you have 16 successes, 16.8 successes? You couldn't. This is the average of it though, right? Theoretical average number of cloudy days. Standard deviation is going to be the square root of 30 times 0.56 times 0.44. That ends up being about 2.7 days. That's your standard deviation. And then how would you calculate the variance? You would square it, right? But we don't really use the variance a whole lot.
What's the 0.44 from?
1 minus 0.56.
Oh, okay.
Q, right? So let's summarize this situation here. So on average, there are 16.8 cloudy days during the month of June. The standard deviation is 2.7. Now, here's where we come up with that idea of unusual months of June, okay? Remember, anything that is more than 2 standard deviations away from the mean is considered unusual. So why is that? Well, it relates back to our empirical rule. So if you have a mean here, now we have kind of a distribution that's kind of looking kind of normal, don't you think? Right? With the mean here of 16.8. But what percent of the data is within 1 standard deviation of the mean, according to the empirical rule? 68% is within 1 standard deviation of the mean. And 2 standard deviations, 95, and 3 standard deviations, 99.7. Okay, so here's what's going on. If I went 2 standard deviations to the left from there and 2 standard deviations from the right, then you have a 95% of the distribution here. What creates an unusual situation if the chances of it are 5% or less? So the chances of being between here and here is 95%. So what's the chances that something would be beyond this value and this value? 5%, so we consider that an unusual one. So what would we do? 16.8 minus, I'm going to put it right here, 2.7s. So if you go 16.8 minus that, you get 11.4. So a year or a month of June that has less than 11.4 days would be considered unusual. Less than 11.4 days that are cloudy. Because that value is what? 2 of these below the mean. Or 16.8 plus 2.7s would end up being 22.2. So if you had 24 cloudy days, based on what we're doing here, that would be an unexpected or unusual month. Because the typical month has got about 17.8 or 16.8. Okay. So that's how you would use the mean and standard deviation to describe maybe that situation that is binomial. Okay. So make sure that you have Wednesday stuff done. Have some work shown, especially for 15 and 16. Okay. Make sure you know how to work on it, and then finish this up as well for tomorrow. Okay.